Waves can be classified into two categories, longitudinal or transverse. Longitudinal, we are talking about sound, or if you've got a slinky, you can exhibit all the types of waves if you are oscillating in the same direction as if you're oscillating in the same direction as the wave is propagating. That's longitudinal. Transverse, your movement is oscillating perpendicular to the direction of the wave's propagation. Most waves propagate. This is a word will come up time and time again. It means that the energy is being transferred in that direction. Most waves propagate through a medium at a speed equal to the product of their frequency and their wavelength. Right, this stands to reason. If we have a wave passing down a string and it's, say, 1 meter wide, it's got a wavelength of 1 meter, it's 1 meter long, rather. And this pattern is repeated over and over again. If a casual observer at the side notices that 50 waves go past per second, they can then deduce, look, there's 51 meter waves going past, therefore the wave as a whole must be traveling at 50 meters a second. You just multiply those two numbers together. Frequency multiplied by the wavelength. This is called the wave equation. In the bottom left here, the velocity is equal to the frequency times the wavelength. But there's nothing too fancy to it, really. Never forget that it is really just a function of if you've got constant wavelengths at a constant frequency, you could just multiply those two together to work out the speed of the wave. Light is a special case. It has a fixed frequency, fixed velocity in vacuum, which is made famous by the letter C. C for celeritas, which just means very quick in Latin. So, and they're not wrong, to be fair. What other equations might we come across? The frequency is inversely proportional to the period. That's by definition. If I say, my observer said there were 50 waves per second, that implies that each wave takes 0.2 seconds to pass. So period and frequency are really just two sides of the same coin. Okay, and I'll just also point out, in case it wasn't obvious, the velocity and therefore the frequency of the waves is dictated in part by the medium in which the wave propagates. So light in air has a certain velocity, but if you put it in glass, it'll go slower. How much slower? Well, that's what the refractive index measures. The higher the refractive index, the slower light will travel through that medium. But more on that later. Very quickly, reflection, refraction, and diffraction, all behaviors we should have encountered earlier on in our school adventures. Refraction is the change in direction of a wave as it enters a new medium. So if you consider waves, we've got Huygens sort of secondary wave fronts coming in here at a certain angle. As this wave front hits the edge, some of the wave now travels a bit slower, and so it doesn't travel quite as far. Like here you can see the edge of this wave is just hitting the medium, whereas these points in the same time frame as they did before, they're traveling the full distance here. These points here unfortunately don't have that luxury, and they can only travel. They can only travel a smaller distance to form a sort of bent wavefront there. And so on and so forth. They progress at a slower rate. And as more and more of the wave here hits the surface, more and more of it gets slows down. And the net result is that these wavefronts get closer together. And you can see that their angle also changes. Purely geometrically, you can derive the fact that that they slow down. Well, if you're given the information that light travels slower in a medium, you can derive the fact that it will change direction and its wavelength will decrease. Sorry, I think I said a few slides ago that the velocity and therefore the frequency is affected. Or did I say the wavelength? I hope I said the wavelength. Yes, if light goes from air to glass, it will get slower and its wavelength will change, its wavelength will decrease. Right. How much will it change by? Okay, so if light is incident on a surface at an angle I, what angle will it refract at? Angle R. Well, it depends on the ratio of the refractive indices. So our incident material, Ni, and our refracted material, Nr, the relationship between the angle and the refractive indices is given by this Snell's law. You may also see it, and I actually personally think this is a slightly more helpful way to write it. You may also see it in its expanded version where you sort of ignore the velocities, although that is also an important statement. You can write it in this form instead. And that's nice because all of the indices for the first medium are on the left-hand side, all the indices for the second medium are on the right-hand side. And it's nice and clean. Whereas this form, you need to be careful. The ratio of the angles, sine I to sine R, is the opposite, is inverse to the ratio of their refractive indices. I is on the top here, but I is on the bottom here. Now, having said that, I is back on top when you talk about the velocities, but that's another point entirely. Whereas if you write it in this format, I think it's just a lot nicer. Diffraction. So we've talked about refraction. Diffraction is the spreading out of wave as it passes through a sufficiently narrow gap or around an edge. And if the gap is too large, you won't really see any significant diffraction. If it's too small, it just won't make it through. And there won't necessarily be that much diffraction, but there's maximum displacement when the gap L here is of a size roughly compared with the wavelength. Okie dokie. And as for reflection, hopefully we're familiar with reflection. You know, the angle of incidence is equal to the angle of reflection. Okie dokie. Exam question. Light traveling through air is incident on a layer of glass at an angle of 45 degrees. The refractive index of glass is 1.5. Good. Refracted light then enters a layer of perspex with refractive index n equals 2. Oh, how exciting. Calculate the direction the light travels through the perspex as the angle it makes with its normal. You may assume that the perspex and the glass are flat and parallel to each other. Good, I was about to ask. Right, it's 3 marks, so it should be 3 steps. It's a calculation question. And the context is that you'll probably need Snell's law because they're mentioning refractive indices. Okie dokie. We've got this diagram like this. We're going to do this, perhaps what I might say the thorough way. And then I will show you a little shortcut that also proves why my rewriting of Snell's law is perhaps a little more friendly. Okay, we're told this is incident at 45 degrees. This is air. Air has a refractive index. You can assume it is 1. In reality, it's very, 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 very slightly different from 1, but don't worry about that. It's more or less the same as vacuum. And we are told the refractive indices are 1.5 and 2. Good. That makes sense. My light is coming in at an angle here. The right-hand side of its wavefront is sort of going into the... You can imagine it. In my head, I always imagine it like a truck driving into a puddle or something. It's aquaplaning. The right wheel of my truck is reaching the puddle first, and so the truck pulls to the right. It pulls closer to the normal. And the same thing happens here. You're going into even deeper water. Oh, dear. Okay. Right. Instant angle of 45. We'll then get the first angle here. And then by opposite angles, we'll get R1 is also our second incident angle. And we'll end up with R2 down here. And this is our goal. It asks, calculate the direction the light travels through the perspex. Okay, right, to calculate R1, write out Snell's law. The ratio between the refractive indices is inverse, is upside down, inverse to the ratio between the sine of their angles. Okie dokie. Plug in the values from the question. So N2 for our first barrier is 1.5 and 1, and the angles are 45 and unknown. Rearrange sine R1 is equal to sine 45 over 1.5, and that gives us an angle of 28.12. Nice. This is 28.12. Okie dokie. Recognize that at the second interface, as we pointed out before, what was the angle of refraction from the first interface, we're going to reuse that angle as the angle of incidence at the second interface, and do it again. The ratio of the refractive indices is inversely proportional to the ratio of the sines of the angles. So this time we've got 2 over 1.5 rather than 1.5 over 1. That's equal to sine 28.12 over this angle, which we want to calculate. Repeat, rinse and repeat. And we get an answer of 20.7. Okay, not too bad. Now, the only thing I want to point out as a slight sneaky shortcut is that if we use Snell's law instead in this cunning guise of n1 sine theta 1 equals n2 sine theta 2. That's complete. That's mathematically sound for the first interface. Hooray. And then for the second interface, I can write n2 sine theta 2. And bear in mind that this angle really is the same as this angle because we reuse that angle, this angle of refraction as our angle of incidence here. And that must be equal to n3 sine theta 3. Well, this is theta 3. If you write those two equations out, both of which are true, you may spot that these are identical. Therefore, we could actually be sneaky and cut out the middleman. Just right. That equation. A little bit sneaky, but it's true and it does work out. Put it into your calculator. It's as if, even if this layer wasn't here, if it had gone straight into the perspex, that zone, that green zone, you'd end up with the same angle, which is kind of neat.